Good morning, class. Or I guess it's afternoon now. Good afternoon, class. And welcome to our second last lesson in physics. Today we're going to talk about mechanical energy for a little bit, and then we're going to talk about pendulums and how mechanical energy and pendulums are related. So let's just quickly review mechanical energy. It's for times that objects have potential energy and kinetic energy, or if they have one or the other. Remember that the sum of the potential and the kinetic energy is equal to the mechanical energy, and throughout a system, that mechanical energy stays the same until you start losing energy to work or to friction, or if you were to get energy implemented to the system. But we're going to talk about that in Physics 20. So this mechanical energy is just made up of EP plus EK. So let's do a quick example. Let's look at 3 different points of an object being dropped from 4.52 meters above the ground. So I'm just going to draw it over here. Something like having a cliff and dropping something where that height from here all the way down here is 4.52 meters. And this is 3 kilograms. Now from the moment that it's dropped, before it gains speed, that's just right here, at this point here, notice how it's not moving. So we have a kinetic energy of 0. Remember, kinetic energy is 1/2 mass times the speed squared. And if speed is 0 here, then the whole thing must be equal to 0. So our kinetic energy is 0. But if you remember the EP formula of m times g times h, mass is not 0, gravity is obviously not 0, and the height is 4.52, so it is not 0. So EP does not equal 0. So we only have EP up here. So let's look at our total mechanical energy, which is EP plus EK. But our EK goes to 0. So EM is equal to EP, which is mgh, which is 3 times 4.52 times 9.81. Gives us 133 joules as our total mechanical energy at point 1. Okay, now let's look at point 2, which is halfway between the ground and the dropping object, the dropped object. Oh no, the dropping point, of course. Between the ground and the dropping point. So that would be right about here. And our height now is equal to 4.52 divided by 2, because it's half of that height, which is 2.26 meters. Excellent. So, at that point, this point here, do you think it's moving? It should be moving, it should be dropping. So our EK is not going to equal 0. Do we still have height to fall? Well, yeah, we're still going to fall 2.26 meters. So our EP does not equal 0. So our total mechanical energy, which is still made up of EP plus EK, and this is actually at point 2. I'm going to change this here to be at point 1 for each one of these. This one is going to be made up of mgh at point 2 plus 1/2 mass times velocity squared at point 2. And that's what EM2 is made up of. Now if we wanted to put numbers into this, we have everything. We have mass, we have gravity, we know our height. we know our mass, but we don't know our velocity. However, we do know the value of EM2. Because, if you recall from before, mechanical energy is conserved. The sum, so EP plus EK, always equals this mechanical energy, and it does not change. So our first mechanical energy is the same thing as our second mechanical energy. So 133 is equal to all this. We're not going to go through the math of that. I just wanted to show you kind of how that mechanical energy stays the same. Now let's look at the energy just before it hits the ground. I'll use red. Right there. So it has a height of 0, which tells me our EP, which is m times g times h, if that h is 0, then that whole thing equals 0. So our EP equals 0 in this case, but EK, this is right before it hits the ground, that's where it has its maximum speed, is going to be 1/2 mv squared. So it does not equal 0 at the bottom, because it's built up all that speed. All the potential energy from the beginning has been converted into kinetic energy at the bottom. So our EM2 is equal to, well, sorry, this is actually 3. EM3 is equal to EP3 plus EK3. And this is 0.3, which is equal to 0 plus 1/2 mass times that velocity, 3 squared. And what does that EM3 equal? Well, it's going to be the same as EM1 and EM2, because that is the law of conservation of energy. So it's going to be 133. We're not going to calculate that, but what you should be able to tell from this whole thing, and the big takeaway, is that at all the points, EM1, EM2, and EM3, the mechanical energy does not change. It's just made up of different amounts of kinetic and potential energies, but that total energy of the whole system is maintained throughout the system as 133 joules. So that's the big takeaway from this lesson. Okay, let's see how this law of conservation of energy and mechanical energy translates to pendulums. Now, most of you probably know what a pendulum is. It is a mass that just kind of swings back and forth, goes like this, back and forth, back and forth, back and forth. Similar to a grandfather clock. If you have your clock here, got this big base, and then there's a pendulum here, and it just goes back and forth 1 second every time it goes back and forth. That's what a pendulum is. Get rid of that because it's not a great drawing, neither is this. Okay, so again, think of the tick-tock of the grandfather clock. In a perfect pendulum, what's going to happen is the mass is lifted off a certain height. So if this were to swing back, it would be at equilibrium here, meaning this is where it would be if it was just still. If you were to pull it back, it would go up here and then swing back and forth. But in a perfect pendulum, this would go once and come back and end up exactly where it started. It would not lose any energy. So that's what we're going to look at for Science 10, is perfect pendulums only, where it goes one way and then comes back all the way up to where it started. Perfect. We can analyze this using energy. Actually, I'm going to leave that there for a second. One big thing about pendulums is that the height that we measure a pendulum with is based on the height of where it was when it started. So our height, in this case, is here. It's gone up that much height since the beginning of the pendulum. So since the equilibrium position. Okay, so H is always measured there. Now let's look at an example of one. We have a 500 gram pendulum, which just means that this mass is 500 grams. And it's lifted 20 centimeters from the bottom. So that height here is 20 centimeters. So I'll just quickly draw another one here. A lot of the times I'll draw it with dots. And this is going to be 0.2 meters. Again, we want to convert that to meters. And we want the total mechanical energy. Well, mechanical energy is equal to potential energy and kinetic energy added together, which is mass times gravity times height plus 1/2 mv squared. Now if you'd like to try along or with me, if you have a string or like a mouse to a keyboard, or sorry, to a computer, that you can just grab one end and then let the mouse kind of be a pendulum, you'll notice that at the top something happens. It changes direction, and for a split second at the top there's no movement. At the very top, when it goes all the way up, or when you're pulling it back before you let go, it's not moving. It only has potential energy. So there's no movement at the beginning. When it's lifted and is about to be dropped, it has no kinetic energy. It's only potential energy, which is, if we change this to kilograms, 0.5 kilograms times 9.81 meters per second squared times our height of 0.2 meters. We end up with 0.981 joules. And that's our total mechanical energy for that pendulum. Now notice how I started it here and not somewhere in the middle. It's because the ends, this point here and this point here, have really special properties. So let's take a look at those in 3 different positions. So obviously this pendulum is going to move this way, and this is its equilibrium position at number 3 there. So at position 1, it's the highest point it's ever going to be. So it's the highest point. There's also potential energy. It does not equal 0. At the highest point, it's also where it changes direction, and for that split second, it stops moving. So at that highest point, our kinetic energy is 0. Because again, 1/2 mv squared is equal to kinetic energy. And if this speed goes to 0, the kinetic energy goes to 0. So at the highest point, EK is equal to 0 and EP is not equal to 0. Let's skip to position 3 here. At the lowest point, well, our height, remember, it's measured from the equilibrium position. That's height. So at this point, our height is equal to 0. At the highest point, remember, V was equal to 0. But the lowest point, our H is equal to 0, which means EP, which is mgh, equals 0. And our kinetic energy, well, at that point, it's moving. It's going this direction, so there is kinetic energy. So that does not equal 0. This is where the pendulum moves the fastest. because at this point, all that potential energy up here has been converted into kinetic energy, and it's 100% kinetic energy at the bottom, meaning V is the maximum amount. Now if we move to position 2, which is here, well, it's in the midpoint or somewhere in between. Our height is clearly not 0, and it's moving because it's on the way down. So your speed does not equal 0, which tells you EP does not equal 0, and EK does not equal 0. So your mechanical energy is made up of both parts. So I'll write our mechanical energies over here. In green. So EM1 is made up of entirely of potential energy. Position 2 is made up of both. And then position 3 is made up of only, oh, this should be not equal 0, only kinetic energy. But, once again, EM1 equals EM2, which equals EM3. Mechanical energy is conserved. So in general, at the top there is no kinetic energy. It's all potential energy. At the bottom, there is no gravitational potential energy. This is the maximum speed. In between the top and the bottom, there's both. EM equals EP plus EK. And then mechanical energy is the same at all 3 points. So let's try another one, or an extension of this one. So if we recall that our mechanical energy is equal to 0.981, and we want to find the maximum speed. So if I was to draw this pendulum again, this is our equilibrium line, right there. We want to find out what the maximum speed is. We know that the EM at the beginning, or throughout the whole system, is equal to 0.981 joules. Well, as this moves, there's only one point where we have a maximum speed. And that maximum speed happens right here. So that's going to be our second point of time that we're going to look at. This is going to be our first. Remember, EM1 equals EM2. So let's look at it the same way we did last time. 0.981 joules has to equal the mechanical energy at this point, which, if you recall, our H is 0, meaning our potential energy is 0. Come on. So EP plus EK becomes 0 plus our EK formula is 1/2 mv squared, which is 0.981 equals 0 plus 1/2 mv squared. If we put in our mass was 500 grams, so 0.5 kilograms. Times v squared. We need to solve for v squared, or v. We're going to first multiply both sides by 2 to get rid of that half. You're going to get 1.92 or 1.962 equals 0.5 v squared. We're going to divide both sides by 0.5. Just going to carry on over here. We get 3.924 equals v squared. Square root both sides. You get v is equal to 1.98. meters per second. And that would be our final answer. So the maximum speed of this pendulum is 1.98 meters per second. Excellent. Hopefully that didn't confuse you too much. If it did, let's just try another one, see if that helps. Alright, if a 3 kilogram pendulum has a maximum speed of 2, what is the maximum height it will reach? So, this is our pendulum here. This is its equilibrium position. We want to know, what is this height here? Well, we have two different points in time to look at again. We have one here, and we have one here. We know that the mechanical energies have to be the same. So EM1 equals EM2. EM1 over here is at the maximum height. Remember from before that at the top of a pendulum, at the maximum height, there is no kinetic energy. So at EM1, our EP1 plus EK1 becomes mgh plus 0, because that kinetic energy is 0. There's no speed at the top of a pendulum. At EM2, which is where the has a maximum speed, recall from up here, the maximum speed happens at the bottom of the pendulum, which is down here at position 2. Our EP2 plus EK2 becomes 0 because the height is 0, plus 1/2 mv squared, because at that point we have velocity. So if I just made this a little simpler, mgh should be 1 equals 1/2 mv2 squared. We want to solve for this h here. So we'll divide mg from both sides. You get h is equal to 1/2, the masses cancel, times v2 squared divided by g. If we put numbers into that, 1/2 times 2 meters per second squared divided by 9.81 meters per second squared. You end up with 1 divided by 9.81, 0.102 meters. Oh, but two significant digits, we have a height of 0.10 meters. or you could write 10 centimeters. Both would be fine. Excellent. And let's do one final one. We're given that the total mechanical energy of a pendulum is 250 joules. So EM equals 250. And we're told the mass is 5 kilograms. We want to know what the max height is and what the max speed is. Let's take a look at our pendulum. So, at the highest point up here, we have some height. And at the lowest point here, we have no height, but we do have speed. I'm going to put this as 0.1. I'm going to put this as 0.2. Let's look at number 1. EM1 is equal to mgh1 plus 1/2 mv1 squared. Now right away there's a few things we need to identify. At this highest point, our speed is equal to 0. So this becomes 0 because this v is 0. So EM1 is just equal to mgh1. Now the second thing is we don't have EM1 and we don't have H1, so we can't solve for this question yet. But recall that the total mechanical energy of the pendulum system has been given to us. EM is equal to 250 joules. EM is equal to the same thing at every point of the pendulum. So this can be replaced by this. 250 equals mgh1. Now we can solve for h by dividing by mg. You get 250 divided by our mass of 5 kilograms joules times 9.81 meter per second squared. That's going to equal h1. If you calculate that out, 250 divided by 5 divided by 9.81 is 5.097, or 5.10 is our total answer. Meters. So that's a very large pendulum. Alright, now let's look at the maximum speed. We know that happens at position 2. So our EM2 is going to equal mgh2 plus 1/2 mv2 squared. Once again, at the bottom of a pendulum, there is no height, so this is 0. EM2 equals 1/2 mv2 squared. This EM2 is the same as EM1, which is the same as the total mechanical energy. So again, 250 joules equals 1/2 mv2 squared. We need to isolate for v, so we're going to multiply both sides by 2 to get rid of the half. Get 500 joules is equal to mv2 squared. Divide both sides by m. You get 500 joules divided by m equals v2 squared. We're going to square root both sides. And I'm going to move it up here. We get square root of 500 divided by our mass of 5 kilograms is going to equal our V2. Which is going to be 10. So it's going extremely fast. At the bottom of the pendulum, we need an extra significant digit there, so I will make that 10.0 meters per second. And that's our total answer. Awesome. Well, I will have the last lesson, which is just on graphing mechanical energy, coming up in the next couple days. For now, please work on your assignment 2 for physics. And please, please, please ask me any questions that you have. I am at my computer all day, and I am just there to help you. So please get a hold of me either on email or through Discord. Have a great day.